Hi. So today we're going to test our knowledge of the last few lessons, which was about springs and energy in springs and gravitational potential energy. By the end, you will have tested all the knowledge relating to this. But let's start off with some simple questions in the form of a starter. I missed a letter out there. Let's put this pen. What is Hooke's law in words? What is Hooke's law as an equation? What are the two ways to work out the spring constant? What are the two ways to work out the energy stored in a spring? Actually, there's three ways. But what are two ways? And what is the equation for gravitational potential energy, GPE? Answer the questions. If you can remember for the fourth one, if you can work out the three ways, that's even better. And then unpause when you're done. Done? Splendid. Hooke's law in words is basically the extension of a spring is proportional . What is Hooke's law as an equation? Nice and simple. F equals kx. What are the two ways to work out the spring constant? Well, one way is to rearrange the equation. So F over x equals k. And the other one is to do the graph of F over x and work out the gradient of the straight line. And that gives you Hooke's law. What are the two ways to work out the energy stored in a spring? There's actually three ways, but I suppose maybe one way's equation, and so we can do E equals half kx squared or half fx. So that's one way, and the other way is if you do the graph, looks like this. You do the area under the graph. And what is the equation for GPE? The equation for GPE, gravitational potential energy, is mass times height times the gravitational field strength, which is 10. Okay, so now we're just going to do some questions. Answer the questions. Make sure you number them really quickly, clearly, so it's easy for us to feedback and help you. We have two force extension graphs. Here we have this one. We have a very kind of steep graph like this, which, note, it takes a lot of force, produces almost no extension. So something you push, work hard on, doesn't really change. And the other one here, we have a particular shape of graph linked to a very specific material. One, a suggested material that would produce a force extension graph like A. It's a very common force extension graph. If you're not sure, you can just Google it. Force extension graphs, different materials. You'll find one that looks like that. Suggest a material that would produce a force extension graph like B. Again, if you've done that for the first one, it will be very easy to work out the second one. B is a very classic material. A, there's multiple things that could fit with the answer for A, but have a go. Describe the difference between plastic deformation and elastic deformation. Again, you just have to go back over the lesson. If something behaves in an elastic way, what happens? Something behaves in a plastic way. The important thing is, when you're writing, always remember to talk about removing the force. Removing the force. So, number 2. A rocket of mass 1,200 kilograms is ready to launch from the platform in Florida, USA. The gravitational field strength on Earth is 10 newtons per kilogram, which is also the same in Florida, in the USA. Calculate the gravitational force on the rocket on the Earth's surface. Show your working and give the units. Use the equation. Gravitational force is equal to mass times gravitational field strength. It's really easy, but don't just write the answer. Write down the working and put the units afterwards. Explain why launching the same rocket from the surface of the moon rather than the Earth would affect the minimum energy required to launch the rocket to a height of 1.5 kilometers. How is it going to be different if you try and launch a rocket on the moon than if you launch a rocket on the Earth? We're not thinking about in terms of being on the moon. Think about the gravitational field strength of the moon and the gravitational field strength of the Earth. Those are the things you need to focus on. Okay, splendid. If you're in school, you would have done this experiment, but you're not, so you didn't. Maybe some of you did it on the FET website. A student used the apparatus shown in the diagram to investigate how a spring stretches when a force is applied. And here we have, here's my spring, like this. I've hung on the end of the spring the little 100-gram masses, and each time you go up in 100 grams, you're increasing the force. It's a ruler that's fixed in position, some clamp stands to keep it all safe. Use a graph to calculate the spring constant of the spring and show you're working. Yeah, I've told you how to do this multiple times. You can work out, use a graph. If I just draw this line, hopefully that'll make it a bit easier. It's quite slow. Hopefully that'll make it easier for you to work out the spring constant. For part 2, use the spring constant that you've calculated and calculate the energy transferred in stretching the spring to an extension of 20 millimeters. If you didn't, they've given you a value here. But note the value they've given you here and the units. There's more than one way to work this out. Please, most important is show you're working. Same equipment, same graph. What force corresponds to the spring's limit of proportionality? Where on the graph does the spring stop being proportional? Where is the limit of proportionality? Is it at 2 newtons? Here. Is it at 10 newtons? Here. 12 or 14? The student concluded that the spring obeys Hooke's law until the limit of proportionality is reached. Is she correct? Is she? Explain your answer. Saying yes or no doesn't mean anything unless you quantify or qualify what it is you've said. Is she correct? Yes, she's correct. Because. Is she not correct? No, she is not correct. Because. The student repeats the experiment using a spring with a higher spring constant. Describe the effect this has on the results. I think the easiest way to do that is maybe describe the graph. Maybe you could even draw what the graph might look like. If you sketch this graph and then sketch what the graph would look like with a spring that has a higher spring constant. We talked about when you have different spring constants. Higher spring constant. Does that make the spring more stiff? As in harder to shape, or less stiff? Two warehouse workers are lifting boxes onto a shelf. Worker A is lifting 1 kilogram boxes. Worker B is lifting 2 kilogram boxes. Worker A managed to lift 30 boxes in an hour. Worker B managed to lift 15 boxes in an hour. Which worker did the most work against gravity in the hour? So, work out the work done against gravity for A, work out the work done against gravity for B, see whose is biggest. Show you're working. Then make a comment on who did the most within the hour. This would be a kind of 6-mark question, so if you've only written 2 words, you're not doing it quite right. And that's it. Good luck. Answer the questions. I'll give you them next time. Bye.